Okay, so we're going to start off by talking about design. There are two kinds of design. There's engineering design and then there's aesthetic design. Your car looks aesthetically pleasing and so does a Chesterfield, whatever. But engineering design has to look at the physical limits of whatever it is you're trying to do, of the materials, for example. So when engineers are working on a design, they make sure the methodology to do all their calculations and come to the conclusion is correct. The methodology has to be correct, and then they take whatever answer comes. And so in Nobody's Fuel, we start at the beginning of what are fossil fuels and follow the logic right through, and the answer is we need nuclear fission energy if we're going to provide energy for everyone on Earth and now. And that's a conclusion based on logic. It's not because I like nuclear. That doesn't matter. It's what the logic leads to that is important in every engineering design. Sometimes I've been accused of being paid by the nuclear industry to say what I'm saying. And that's in fact not true. I'm completely independent. I'm a retired mechanical engineer. I spent 17 years basically designing, building, and starting up chemical plants. And I've spent the rest of my career in industrial research. So I've been in industry all the time, none of it the atomic industry, none of it the oil industry, all completely independent. So nobody pays me for anything. So when I come up with a conclusion, it's a solid engineering analysis to get there. And as an engineer, and any engineer knows this, that you have to see the world exactly as it is. Because if you don't see the world exactly as it is, you'll design something and it'll break. One of the problems with energy efficiency is if we become very energy efficient, then it costs less to do certain things. And so people start doing more of them. If the energy efficiency of your car was increased by 100%, so it took only half the gas to do what you do, would you drive the same amount? You'd probably drive more. And that happens time and time again. When energy efficiency increases, we use more energy. But energy efficiency is a two-edged sword. Because we use energy more efficiently, we use more of it. And so total energy consumption goes up, even though we reduce the amount we use for a specific application. Okay, let's talk a little bit about trees. Trees are very important to us. We all like trees very much. And trees were the main source of energy throughout history for many, many times. And many times, people ran out of trees and didn't have any fuel, and either had to move to another area or they just didn't have fuel. So trees are very important were important from that point of view, but they're not nearly as important now because we've replaced trees with fossil fuels. In the United States today, there are more trees than there were in 1850 because the U.S. stopped using trees for fuel, so now they can grow. But if there's a shortage of fuel, shortage of oil to heat your house, all those trees that we like are going to disappear into somebody's furnace. You may have seen a TV program recently about the Berlin airlift. Maybe you noticed that before the Berlin airlift got started and people were short of fuel, they were cutting down the trees on the boulevards to use as fuel. And that's going to happen if fuel is short. So trees are important to us, but they're not good as a fuel. Let's talk a little bit about the scale of things, because scale is very important. People talk about Brazil as running their transportation on ethanol made from sugarcane. And they do that. They don't use all ethanol. There's some gasoline in there too. But the amount of ethanol that Brazil uses for its fuel supply would last the United States for about 2 days. And that's all. And ethanol is not a very good fuel either. You know, 1 gallon of ethanol has about 3/4 at most of the energy content of a gasoline. So you need a bigger tank, or when you start mixing it with gasoline, as is going on now in California and other places, 10% ethanol, your gas mileage drops by that amount. Scale is important when talking about carbon emissions. For example, if we were to replace all fossil fuel generating stations with nuclear stations, we would reduce U.S. carbon emissions by about 1/3, and that's huge. It's also important to understand scale when we talk about all the little things like changing light bulbs and walking and using a bicycle and all that. We are reducing fossil fuels, but we're not replacing them. We're not replacing them. We extend the time that they're available, but we don't replace them. We need carbon-free energy like nuclear to replace fossil fuels. Today, electricity is generated using a source of energy to boil water, to make steam, to run a steam turbine, to turn the generators and generate electricity. Most of the world's electricity is done this way, 80% of it. The other part is hydro. Hydroelectricity does the other part, with a little bit of wind, but not much. And why do we use a steam electric system, as it's called? Because this is a reliable, durable system that can generate lots of electricity quickly and when we need it. Hydroelectricity is already very good, too. Now, steam electric systems are not very efficient because of thermodynamic laws. About 1/3 of the heat energy that goes in comes out as electricity. Hydroelectricity is about 85% efficient. In other words, 1.2 units of hydropower give 1 unit of electricity. And it's been that way for more than half a century, so we don't expect the efficiency to improve. Improving the efficiency of a steam electric system, which is about 33% efficient, is very difficult because it means you have to increase the steam temperature or lower the cooling water temperature, and that's difficult to do. Now, there are some systems that use natural gas and burn that directly in a gas turbine and use the exhaust gases to generate steam. That's an integrated system, and that can go as high as 66% efficient. And that's good as long as the natural gas lasts, but when it becomes scarce, then those systems will no longer be usable. We'll talk a little bit about storing electricity. The way electricity is generated today in our generating stations, it's a flow of electricity, and it's a continuous flow. And when you need it, if you start the flow into your house, and when you don't need it, you turn the flow off. Now, storing this flow is very difficult. Storing electricity usually requires that the electricity be converted to direct current, not alternating current, and then the electrons go into some kind of a chemical storage system where they fit into molecules and they're there ready to be taken out at some time. And it's a chemical reaction. And you can reverse the chemical reaction, like the battery in your car, and get electricity back. Now, you have to find a place for each electron, because electricity is a flow of electrons. And that's where the limitation comes, is finding a place for each one of those electrons where you can force them into a place, and when they come out, they'll give you that force back. And it's very difficult to do, and that's why there is no really good ways to store electricity today. When we're looking at wind electricity and solar electricity, these are very intermittent and erratic. They don't come when we want them, and when they do coming, they're always changing. So what people say is, if we had a good way of storing lots of electricity, we could just store up the electricity when wind and solar are making it and use it when we want it. And that's why people are interested in storage of electricity, large-scale storage.